Hello! Today we will talk about principal components, how to obtain them. We will see the difference between population and the sample principal components, and then we will test for the correlation structure as well as compute the correlation coefficients. We will start with two simple examples. When we have 2 times 2, so this is our sigma population covariance, and we want to compute out of this population covariance our, in this case, two principal components. How we can do that? Well, we can go first in R and find eigenvalues and eigenvectors. Okay, so you should just type eigen sigma in this case, and then you will get the eigenvectors and eigenvalues. So I just copy them from R. So we have our eigenvector, okay, and our lambda 1 that is corresponding to our eigenvector first, and lambda 2 corresponding to our second eigenvector. What we have is our theorem that gives us how will our principal component look like. So we know that there are linear combinations of elements of our eigenvectors. So basically we want E1 transpose to multiply with x. X here is only x1, x2. Okay, so what we get is this one. So this is our first principal component, and this is its variance. So the variance of our first principal components is 6. Then for the second principal components, we need second vector and second lambda. So we can again see 0.447, 0.47, and this constant is for x2. So those are two of our principal components. Our total population variance is sum of our eigenvalues. So 6 plus 1, 7. We can also compute our 6 divided by 7. Sorry. Just go right click and show as numbers. So format cells and numbers instead of date. So this is the proportion explained by the first principal component. So in this case we can say, only based on this, that we can take only first principal component and in that way remove one dimension. As you can see, it is simple when you're given the population covariance. Let's see when we have the sample covariance, would something differ? Well, in this case only our notation was different basically. So instead of our population, we have our covariance matrix. We did numerous examples how to compute this sample covariance matrix. So in R you should just type eigen s, and it would return eigenvectors and eigenvalues. You can interpret them as well, but instead we get the sample principal component. So in this case 2. Also we mentioned our coefficients, correlation coefficients. So correlation coefficient between our first principal component and our x1 is given by, so first element of our eigenvector times square root of the first eigenvalue divided by square root of our variance. So it is given here. We can see. So this is E1, 2. For 1, 1, this one is E1, 1. So we would need that one. This one would be E1, 2. Actually, this one is E1, 2, and this is E2, 1. So E2, 1, E2, 2, E1, 1, E1, 2. Okay. So we can see that the correlation between our first principal component and our x is high, really high. What else we can see is, for example, when we divide our variance of our first principal by the sum, so by the total, we would get something extremely high. So we can either be sure that we can eliminate x2, or we would like to, instead of our covariance, sample covariance matrix, we would like to use the correlation matrix. It might give some other result. Okay, so those two are really simple two examples for our population and our sample covariance matrix. Okay, let's do another kind of simple example where we test for equality in correlation structure. So based on our correlation matrix, we want to use the only test that we mentioned, so that our matrix rho is equal to rho 0, where rho 0 is all those elements are equal. So let's actually see how it looks. Let's move to PDF. Okay, so here you can see actually the test. What are we using? So we need to compute all of these values that you see on the screen. So RK, R, gamma, our T statistic, and then our critical value based on P plus 1, P minus 2 divided by 2 degrees of freedom with some alpha. Okay, so you can open this so you can follow in Excel. Okay, let's go to Excel. Let's first compute our RKs. So our RK bars. So RK bars are those over here. Okay, so we actually need to sum all of those without first one. So without our, because it has to be different. So we are summing over all RAK. Okay, so by I, but I should be different than K. I think it's not written in PDF, but yeah, I should be different than K. Okay, so we just do not need the diagonal elements. Diagonal. Okay, so in order to do the same for everything, just to move it, we will just subtract 1. So if we subtract 1, we will actually get the sum of all the rest, right? Which is what we actually need, sum of all the rest, just not the diagonal ones. So we need sum of all minus 1. So sum of all minus 1. In that case, we always sum just those. Okay, then we need R bar. So we need to, so double sum, I goes from 1 to P, and I should be less than K. Right, so it would be just this one, this over here, right? And then just multiply by 2. So if we multiply by 2, we get this side, right? So basically now we have sum of all those plus sum of all those, and then divide by P times P minus 1. So it is 5 times 4, it's 20. Okay, so this formula basically gives us the same. So we sum all of those, then we subtract those, okay, and divide by 20. Just a compact formula to compute it, nothing special. Then what we need is our gamma, right? So we need this gamma. This gamma can be computed only using our R bar, only using this. So it is P minus 1 squared times 1 minus 1 plus R squared, right? So this is basically what it says here. I believe I missed a square on the paper, on the PDF, so just here it should be squared. So this formula in Excel is correct. In the PDF it is not. So to compute our T, we would need our differences. Then we need to square our differences. So difference between this and our RK, and we need squared. We need our gamma, right? And we need the differences. So RK bar minus R bar. So this is what we also need. We already know how to compute those, so I will not talk about the formulas in Excel. Should know this by now. So what we have here, okay, is our RIK, so those, minus our R bar squared, so those. And we need to sum over all, but not diagonals and not the same. So basically just those here. We need some of those. So we can see here that we do sum of those, sum of those, sum of those, sum of those, minus gamma times sum of our differences squared, but differences squared of this minus. So this is RK bar minus R bar. And the last what we need is our chi-square critical value for this significant alpha 0.01 with degrees of freedom p plus 1 p minus 2 divided by 2, and our p is 5, so 6 times 4 divided by 2, right? Sorry, 6 by p minus 2, so 3 divided by 2 is 9. So this is our right tail of our critical chi-squared. As t is larger than our critical value, we reject null hypothesis. So the correlation structure that we tested for, we can reject it. So the null hypothesis. So here, so this. So we rejected null hypothesis. Then we can conclude that our eigenvalues are different actually. Or at least it's not in this particular correlation structure. Okay, and let's go to interesting problem. So where we have actually 5 variables. Let's see how we can reduce dimensionality to this data. Okay, so what we want to do is first compute sample covariance matrix, because now we have data. So far, we had a simple covariance matrix given. Okay, so we know how to compute it. We already talked about that, so we will save time. Then what we need to do is find in R eigenvalues and eigenvectors of S using this one. What it returns is our lambdas and our eigenvectors. However, in this case, in the first case, when we use the sample covariance matrix, okay, we'll just talk about our lambdas. We know how the principal components look like if we have our eigenvectors. So what we can see here is that the first eigenvalue dominates. Okay, so it is fairly large. It explains 95% of the total variance. 85, sorry. So 85%. How did we get to this number? So what we need is our total variance, which is sum of our eigenvalues. So this is this one. And then we just divide each of variance by the total. And here we have cumulative. So we see that first two principal components would explain, so 94%, but even 85 is fairly enough. Okay, so why could this be the reason? So we can see that some variables might be have higher variances in compared to another. So it might be due to scaling. So let's see if we, instead of those variables, if we use our standardized variables. To standardize the variables, so we will need mean and the standard deviation. So this is the mean of this variable and the standard deviation, but using formula divided by 20 instead of 19. Okay, so what we have here are our standardized variables. So z1 it would be x1 minus x bar divided by snii. Okay, so those are all standardized variables. Now that scaling factor does not exist in this data. What we need then is the covariance matrix of this set of data. We compute it the same way as we did here. but we divide by 20 because we computed this one. So we talked about this in the theory about dividing with n and n minus 1, so you can check it. Then what we need is sample eigenvectors and eigenvectors of our covariance matrix of standardized or our correlation matrix. Again, using R, we obtain this. So those are our eigenvalues and eigenvectors. Okay, so we know how our principal components look like, right? So 0.298 times Z1 plus this times Z2 is etc. So in this case, still we have 5. We also have eigenvalues that, as we know, when we compute from standardized, they equal to P. Our P is 5. So this sum has to be 5 or you have made a mistake. Okay, so those are the variances of our principal component, each of eigenvalues. So the proportion to the first one, so with the maximized variance, is 45%, which is not enough. So we look at the second one, plus 32, so it is 78%. Still, we can take 2, but we would like more. So let's say that we take 3. So they explain 92%. Right. So looking at this, we can choose 3 principal components and reduce to, instead of looking into 5 variables, we will look into 3. Right. So we also mentioned something called script plot. Okay. So for this script plot, we would like to see something like an elbow shape on your hand. So elbow. When does this become like? So we still would choose 3. So based on the script plot, 2 would not be enough, so we would like 3. So this is, or even 4. But yeah, 3 is much better. So this is where our shape becomes. So what we plot here is our 1 corresponding to the first, 2 corresponding to the second, 3 corresponding to the third. Okay, so this is our script plot. It also suggests to pick 3 principal components. So let's say that we pick those 3 principal components. How will they look like? So our y1 would be linear combination of this vector, right, and our z1, z2, z3, z5. We could also compute values of the principal component. How do we compute those values? So remember that this is our data now, so standardized. So what we would like is to multiply so each of those with this. So basically what we do here is multiply each of those with z1, so with corresponding values. So e1, 1, so this one times z1 plus this one plus this one. So basically you're using the formula that we have for the principal component. Then the following would be this times corresponding, right? What we are actually doing is multiplying this matrix with this matrix to obtain our values of the principal component. This is what we need in the end to plot. So for example, if we choose only 2 principal components, we can plot them. So they become our new axes, so in the direction of our eigenvectors. So we have those 2 eigenvectors. In their direction, we would plot new coordinate system, and then we would plot. So these values are actually corresponding to these values here. So this is a scatter plot of the values of principal component. There is so much more to this, but the course is already overwhelming, so we'll a lot about this. In 3 dimensions, it's a little bit harder to imagine this. There exist special plots called biplots. You can read about this. And as we chose only 3 principal components, so we will take lambda1, lambda2, and lambda3, and we can compute our correlation coefficients. They will give us the correlation between x, so between our principal components and our variables. So in this case, not x, but z. That's z. A little bit better. So the fast way to do it is just multiply this matrix with transposed our eigenvectors. What we actually get is from the formula Eij, for example, times square root of our lambda. So you can look at the formulas in the PDF. That way we compute at once all our correlation coefficients. Then each of these rows correspond to a principal component. So this is air, let's say 1, 1, air 1, 2. So 1 corresponds to the first principal component and 2 to our Z2, Z3, Z4, Z5. So we can see that actually the highest correlation is for Z3 and Z4. So for those two, between our first principal component and our Z3 or Z4. What we can also see here that the values, so in our initial set, the values of those variables corresponding to Z3 and Z4 are the highest compared to the scalings. So here we have some 2-digit numbers and here 1 digit. Then for our second principal component and each of those Z1, Z2, Z5, okay, we can see that, for example, here and here is the highest. So between second one and our Z2 and Z5 is the highest correlation. So then we have 2 and 5 or these two. And in the end, for the third principal component, the first variable. So this is perhaps a good choice. So this would be enough for you to know for the written exam. However, it might be a little bit more complicated if you chose one of the complicated exits. So this is the most simple example, but this should be enough. So this will be it for the principal components. See ya.